Hi everyone, we're going to continue here with chapter 16, which is our last chapter in this term. And this is going to discuss oxidation reduction reactions. And in this particular part of it, it's going to talk about something called oxidation states. So remember the discussion we had about what we call redox reactions, which cover single displacement reactions, combustion reactions, combination, and decomposition reactions. Now, what all those reactions have in common is that one of the reactants will transfer an electron and another reactant will accept that electron. So all those reactions can be considered an electron transfer reactions. Because all those reactions have electron transfer as a common theme, we try to understand a little bit more about how the electrons are transferred and who's receiving and who's giving away the electrons. So we have specific terms to be able to understand redox reaction a little bit better. The first term is oxidation. That's the process of electrons moving away or being given to another reactant. So the reactant that gives away an electron is considered to be oxidized. Reduction is the process of receiving an electron. The reactant that receives an electron, then it's said to be reduced. Two terms are associated with oxidation and reduction, which is oxidizing and reducing agents. Okay, so when we use the word agent, we're referring to the specific reactant that's causing something to occur. So an oxidizing agent is a reactant that causes something else to be oxidized. So the oxidizing agent itself is reduced. The reducing agent, on the other hand, is something that's causing another reactant to be reduced. So the reducing agent itself is oxidized. There's a couple of mnemonics that can help you remember these relationships. So oil rig is a common one. Oxidation is loss of electrons in that case, and reduction is gain. Leo the lion says ger. There he says lose electrons mean oxidation and gain electrons is reduction.
So let's use that idea that we just talked about in terms of electron loss and electron gain and help us identify in a specific reaction what species is oxidized and reduced and what the oxidizing and reducing agents are. So I'm going to look at this second reaction here, which is 2Al plus 6H plus forming 2Al3 plus and 3H2. And the way we use that concept of electron loss and gain is to first count the number of electrons that we have. So aluminum, if you go to the periodic table, has 13 electrons in them. And the way I know that is because this is aluminum element or the atom, and the atom has 13 protons, which means for it to be neutral charge, it has to have 13 electrons as well. Hydrogen here, again, I'm looking just at the hydrogen. I'm not looking at the 6 hydrogen, just looking at each of the hydrogen. And hydrogen here is H plus or the proton, which of course means that it has no electrons, so 0 electrons. Aluminum 3 plus on the product side means that it's lost 3 electrons, so then there's 10 electrons in it. And then H2, now in there is 2 H atoms, they're bonded together. Each H has 1 electron, so that's the number of electrons in that species, per hydrogen element, okay? So then once you have that, all you need to do is figure out what the change in the number of electrons is. So if you go to aluminum, you notice that the aluminum has gone from 13 to 10 electrons, so it's lost 3 electrons. So if it's losing electrons or giving away electrons, that's another way to think about it, then it's oxidized. So the aluminum is oxidized. The hydrogen, you go from left to right, you notice that it's gone from 0 to 1 electron. So that means that it gained electrons, so therefore it reduced. Okay, gain 1 electron. Okay, so then what we can write here is we can say aluminum is oxidized and hydrogen is reduced. And then the next thing we need to do is actually identify the oxidizing and reducing agent. So those are just the actual reactant that causes the oxidation and the reduction. So the oxidizing agent is the one that causes something to be oxidized. So that means the oxidizing agent itself is reduced. So the species that's reduced is H. So the reactant that contains H is H plus. So H plus is the oxidizing agent. And then the reducing agent therefore has to be the species that oxidize, which in this case it's also just aluminum because aluminum in the element form is actually involved in the reaction. So aluminum is the reducing agent.
Now, one of the things about redox reaction is, a lot of times it's actually somewhat difficult to know which reactions have been oxidized or reduced, particularly for covalent compounds. So for example, like this reaction right here, C plus 2S goes to CS2. CS2 is a covalent compound, so the electrons are being shared here, so it's not quite clear going from the element carbon to the carbon bonded with the sulfur whether the carbon has lost or gained electron, because in the covalent compound those electrons are shared between carbon and sulfur. So as a result of having this difficulty of identifying what species is being reduced or oxidized, we have developed a way to account for those electrons, and that method is called the oxidation state or oxidation number method. The idea of assigning an oxidation number or oxidation state to an element is just assuming that if you have an electron that is being shared by two elements, like in the case of carbon and sulfur in this case, that instead of the electrons being shared, you're going to assume that the electrons are being completely given away to the element that is more electronegative. Here is the picture of the CS2 Lewis structure. In the oxidation number assignment, we would assume that all the electrons go to sulfur. So if all the electrons go to sulfur, that means sulfur would have 1, 2, 3, 4, 5, 6, 7, 8. In the element state, sulfur only has 6 electrons. So because sulfur has 2 more, the oxidation number for sulfur in CS2 is -2 because it's 2 more electrons. That's the same with the sulfur on this side. If all the electrons belong to sulfur, that means carbon has no electrons, compared to the original element state where carbon has 4 electrons, now it has 0. So that means carbon has lost 4 electrons, so its oxidation state is +4. So sulfur would have a -2 oxidation number and carbon would have a +4 oxidation number. Using the assignment that I just described, you can apply it to all the other elements and as a result have specific oxidation numbers for various nonmetal elements as well as for metallic elements. Now for metallic elements it's a lot easier because whatever the standard ionic charge is on that metallic element, that's also the oxidation number. But for nonmetal elements it's a little bit more difficult and you have to actually follow a specific set of rules that goes from the top being the most important all the way to the bottom. So you have fluorine, that the oxidation number is always going to be -1. If you have hydrogen, it could actually be +1 or -1. It's generally +1 if it's combined with another nonmetal, but when hydrogen is combined with a metal, it actually has an oxidation state of -1. Oxygen is typically -2. Sometimes it could be -1 if it's a peroxide. And then after that, group 7A is going to be -1, group 6A -2, and group 5A -3. Now if you have SCl2, you're going to have to assign the Cl first before you can assign the S. This is in other words saying that group 6A typically is -2, but it's not always -2. Group 7A is typically -1, but it's not always -1. It really depends on what it's paired up with, okay? This picture right here gives you a complete set of rules to assign oxidation numbers for all kinds of compounds and elements in compounds. So if you have free elements, then the oxidation state would always be 0. So free elements, for example, are copper, Cl2, oxygen, O2, nitrogen, N2. It's just going to be 0. If you have an ion, then whatever the charge of the ion is, that's the same as the oxidation state. An important rule is that if you have a neutral compound like H2O, then the sum of all the oxidation states of all the elements in there should equal to the total charge, which is 0. Like in the case of H2O, 2 times the oxidation state of hydrogen plus 1 times the oxidation state of oxygen should equal to 0. So since H is supposed to have +1 charge and oxygen is -2 charge, that ends up being a correct equation. If you have an ion, like a standard ion or a polyatomic ion, then the total sum has to equal the charge of the ion. So like in the case of the nitrate ion here, NO3 minus, the oxidation state of the 1 nitrogen plus the oxidation state of the 3 oxygens should end up being equal to -1. So that will allow you to find out what the charge is of a specific element. So for example, like in this case, if we have NO3, going back to the rules here, we see that if we look from the top, oxygen has to be assigned first before we can assign nitrogen, which is a group 5A element. So if we go back here, oxygen has to be -2. So if it's -2 and we have 3 of them, that means it's -6. What plus -6 will give you -1? And that number has to be +5. So in this case, my nitrogen has an oxidation state of +5. And so that's an important idea to point out again, that even though here it says group 5A is -3, it's not always -3. So you always have to follow this sequence in assigning oxidation number in terms of the priority. Some metals already have their standard charges, like the group 1A and group 2A metal cations, so those will always have those charges. You're not going to have to change them ever. And then non-metals, as I was showing you earlier, would be assigned according to this chart right here, again with the priority being the most important starting from the top.
So let's work on this problem on how to assign oxidation states using the rules that we just discussed. So I'll pick a few of these species that are listed here to assign oxidation numbers for. So let's try first CO2. This is one where all you have are nonmetals. So then you're going to have to think about that nonmetal series that I was showing you earlier in the notes and use that as a way to assign the oxidation numbers starting with the elements that's highest on that list. If you look at both carbon and oxygen, carbon is not even on the list, but oxygen is. So we're going to start with oxygen, and according to that list, oxygen is going to have an oxidation number of -2. So I'm going to put that on the top there in red just to distinguish that with the numbers that I'm going to write in the bottom. And the numbers in the bottom is just the total charge for all the oxygens there. So each oxygen is -2. So if you have 2 oxygens, then it's going to be -4. I need that because that would allow me to figure out what the oxidation state of my carbon is. Remember that the sum of the two has to equal the total charge of the species, which is 0 in this case for carbon dioxide. So therefore, my carbon must be +4. Let's pick another species. Now let's go with an ion. So we have the sulfate ion, SO4 2-. And again, what we would do here is look at S and O, the 2 elements that we have, and see which one we have to assign first. Again, this is a case where all we have are nonmetals. So we look at the list that I showed you before in the notes, and oxygen appears higher on that list compared to sulfur, which is a group 6A element. So we're going to assign the oxidation state for oxygen first, which is -2 again, and therefore 4 oxygens is going to give us -8. And in this case, it's an ion that has a total charge of -2, so we want to make sure that the sum of the sulfur and the 4 oxygens gives us -2. That tells us that the sulfur in this case must be +6. So for those of you who were looking at that list earlier and saw that group 6A has to be -2, again, I want to remind you that it's -2 if nothing else is present in there that would change it. In this case, oxygen is higher in priority, so that has to be assigned first. Let me try an ionic compound now. So let's take a look at FeCN3. Whenever you have an ionic compound, it's best to separate them out first into the ions. And the way you do that is just by your rules in nomenclature. The iron is going to be separated from the polyatomic ion of Cn. Now, here you remember from nomenclature that Cn is Cn-, so it's really Fe3+ and 3Cn-. And then from there, you separately assign the oxidation state for each of the elements. The iron is obviously easy because it's just a 3+ charge on it, so that's going to be a +3 oxidation state. The Cn-, we can take a look separately in this context right here, just looking at that, right? Because the 3 really doesn't matter. That just means there's 3 of these guys. But to assign the oxidation state of each of the element, I can look at just that one polyatomic ion. Carbon and nitrogen, they're both nonmetals, so we have to go to that nonmetal list and check which of those 2 appear on the higher priority list. Carbon doesn't appear on the list, but nitrogen is the last thing on the list, which is the group 5A. So we're going to assign nitrogen in this case as a -3 because it's a group 5 element. So if it's -3, then carbon plus -3 has to equal -1 because that's the overall charge of that polyatomic ion. So the carbon in this case must be +2. And there you go in terms of how to assign the oxidation state for that compound.